in the mill I have, you see there I have a tilt axis and a rotary axis. And I have an ink pen in the spindle, and that white plastic comes to a point. I just, by eye, I got them to meet up visually correct. And so that's where the point of that plastic is right now. There we go. All three, X, Y, and Z. Now I'm going to rotate, and I'm going to tilt, and we're going to calculate where that point went to. Okay, so let's rotate. What should we do? Let's go, let's just go, I don't know, 5, 10, 15, 20. Let's make it 25 degrees. 25. No, let's go 35. Right there. So that is clearly in a different place, and it moved in an arcing motion. So where is it now? First I'm going to do it the hard way. Okay. Okay, that's better. Okay, inverse tangent. And so we want to enter 0.47. This is where that point was. 0.47 y divided by where it was in x, which was 1.611. Okay, that's how many degrees around the circle that point was, or that would be the angle of the hypotenuse. And we need to know the distance from the center. So we can use let's use the secant, because that 1.611 is a bigger number than 0.47. So there's no secant button. So you just do 1 divided by cosine of that angle right there times the adjacent side was 1.611. And that's how far from the center. 1.678 inches. That's how far from the center of the rotary table that point was. Okay, now we rotated 35 degrees. So we take the angle, the original angle, and we add 35 degrees to that. And that's where the point is now. We know where that point is now already in polar coordinates. It's 1.678 inches from the center, and if you went in the direction 51.264, and you went that distance, 1.678 inches, you would get to that point. But we got to move that ink pen to that point. And that doesn't move the same way. That moves in XY coordinates. So we need to convert back to XY coordinates, which the next calculator I want to show you has. In that calculator, XY coordinates are called rectangular coordinates. Okay, so how we do that? Let's see. Okay, so we need the sine of that angle times the radius that we found, which was that number. That's how far it is in Y. It's 1.309. And we also need cosine of that new angle that it's at now, or that distance around the circle that it's at now, times the radius again, or the length of the hypotenuse. I'm kind of using both. Kind of using full circle and triangle trig. I'm kind of using them both. Okay, wait. Times yeah, this number, the radius, and that's how far it is in X right now. So let's see if it's right. We're going to go to 1.050 X. All right. And we're going to go to sine gave us Y, so that's we're going to go to 1.309 Y. I went past it. 1.30. Went past it again. 9. There we go. Close enough. Okay, so we knew where that point went after we rotated. Now, let me go get the other calculator. I'm going to show you how easy it would have been. This other calculator is a converter. Already over here. Okay, this calculator costs about $20. You can get it anywhere. It has a converter. So what you would have done here is you would have just converted the XY coordinates of where that point was to polar coordinates. And you would do that by pushing, we have rectangle, we want polar. So you ask for polar by pushing shift and the plus key. So it says pole, that's what's going to give us. Let me make sure you read what that calculator is. There you go. FX 115. Okay, so it's going to give us polar coordinates. It's going to convert, but we have to tell it the XY coordinates of where that point was. So it was, and you have to enter where it was in X first. So it was at, I had it written down over there, 1.611. So we do 1.611. And we have to put a comma. It's shift and this bracket, right? Shift and then that bracket. You see, put a comma there. So the comma, now it knows we're going to give it y, the y distance next. And that was 0.47. All right, close the bracket. And when you push equals, that gives us, see that, R, 1.678. Remember what we got? We got, where was it up here? That one, 1.67816. See that? Got the same number. Now if you scroll over to the right, that symbol is theta equals 16.264, 3 degrees, and right here, we got that by doing the inverse tangent. 16.264, 30, same number. Okay, so you didn't have to know trig. With this calculator, I use trigonometry. With this calculator, I just told it the XY coordinates, that's all. And it converted. It does the math. And okay, so now what you would do is you'd write down both of these numbers. And at 16.264, you're going to add a rotation to that. And then you have the radius. Radius didn't change when we rotated. R, it was 1.678. That didn't change. So we're going to convert back to XY coordinates, and we're just going to give that number right back. But what it gave us for theta, we're not going to give that number back. We're going to tell it that we added 35 degrees to that when we convert back. So let's clear this. Now this time we want rectangular coordinates. So that's going to be shift and the minus key. It says rec, meaning that's what it's going to give us. We got to give it the new polar coordinates, which we have right here. It was we got to enter the radius first, which was that number, 1.67816. So we entered at 1.67816. Okay, then we put the comma there so that it knows the next thing, that's the end of that number, and the next number we give it is going to be the degrees around the circle that it is currently. And that is, again, you wouldn't have two calculators like this. You just would have wrote down the numbers that that this calculator gave you. I didn't write them down because I have them right here in the other calculator. So now we're going to give it, see that's the degrees that it was at before we rotated, plus the 35 degrees that we rotated. And it's now that far around the circle. So we tell it that. Let's tell the calculator that. 51.264 degrees. So 51.2643. Close the bracket, push equals, and there's the new x coordinate. There's the new y coordinate, and there's the y coordinate that we got with this calculator right there, 1.309. 1.309. Let's scroll back over. It gave us, the converter gave us for x 1.050, and right there 1.050. So that's how much trig you will not need to know if you get one of these calculators for $20. And my other videos will show you how to give you a model you can use to make wheels and whatever you can think of. But I also want to do a tilt. Okay, now let's do a tilt. 30 degrees to get this out of the way. Okay, I want to do a 30-degree tilt. Seven turns and a half of a turn. Can't really get my head in front of the dial, but it's gonna be close enough for this experiment. And let's bring this back down. Okay. Okay, now let's clear all this out of here. Okay, so we're standing on the right side of the mill, and we're looking at the dead center of the tilt axis. That point is in Z. Let's do the inverse tangent. Z is 3.699 inches. Divided by where that point was before we tilted. And Y, it was 1.309. Put a couple more digits. 033. Okay. That's the angle of the hypotenuse before we tilted. We need the hypotenuse length, or the radius, the distance from the center of the distance of that point from the dead center of the tilt axis. Now in this case, the z-axis is a bigger number, 3.699. So we're going to use the cosecant to find the hypotenuse length, or the radius. So that's 1 divided by sine of that angle right there highlighted, times the opposite side, which is 3.699, and we get the hypotenuse length, or the radius, Now that we're looking at it from the right side, we're standing on the right side looking at the tilt axis. That's the hypotenuse length, or the radius, the distance from the center. Okay. Now, we rotated 30 degrees. So those numbers are where it was before we tilted. So let's take how far it was around the circle. Let's bring that down here. Let's add 30 degrees to it because we tilted 30 degrees. And that's how far it is now around the circle in degrees. Okay, so where is it now? We need to find the sine and cosine of that angle, the new angle after we rotated. Times the radius, which was 3.923, and we get, that's our z-axis, 3.857, and we have to find where it is in y, which would be the cosine of that angle, times the radius and we get, that's where it is in y, and we're going to go to that and see if it's right. And x didn't change. We didn't move that when we tilted. When we tilted, that point moved in an arcing motion in z and in y, but it didn't move in x. Okay, so let's go to it and see if those 2 points line up. So I'm going to do z first. Make sure we don't crash anything. Go to 3.857. 0.857. Wait a minute. Maybe I'll go past it and come back up. So sync. There we go. Okay. We're there in Z. And now we're going to go to negative 0.715, and right above it there, you see 3.857. That's the z-axis. Okay, so we're going to negative 0.715. 2, 3, 4, 5, 6, 7, 1, 5, right there. Negative 0.715. There we go. Those are lined up. I'll get a view of the get a view of it from the right side, so you can see. Okay. get a piece of paper here. I just can't do this with one hand, but well, let's try this. I'll lift the spindle up and down so you can see that. So we're correct in Z also. The quill stop is set. All right. So from every view, we know exactly where that point went. I can't get it in there. Okay, now the same thing with the other calculator. That's how much trig you didn't need to know. Because with this calculator, you would have done it very different. Okay, maybe this light needs to go off. That's better. Okay, with this calculator, you would have done, you would first ask for the polar coordinates of where it was before we tilted. And you would have entered the XY coordinates before we tilted. Those were, I'm trying to look over here to my right here. The XY coordinates were, you always got to enter X first. Okay, so 1.309. And 033. All right, then we get the comma. Okay. And now we enter where it was in Z. That was 3.699. Making sure you can see. Close the bracket and push equals. And see, R is 3.923. And that is right there. Oh no, right there. 3.92379. 3.92379. Okay, let's scroll over. Theta, that's the angle, 70.51172. Where's that? That was up here. Right here. 70.51172. Alright, so this calculator did all that trig for you. All you had to do was enter where it was in XY, and it gave you the other set of coordinates, radius and theta. Distance from the center and distance around the circle or the angle. Okay, now, okay, so we tilted though. So let's clear this and let's ask for, so now we already know the new polar coordinates, because you just add in, the radius doesn't change, so that's still 3.923. That doesn't change when you rotate or tilt. And the distance around the circle is now how far it was plus another 30 degrees, which is 100.511 degrees. Right there. Again, you would have written all this down. I have the other calculator, so I'm just looking back at it instead of... I mean, I wrote some of it down too. I have some of the numbers written down on paper too, just so I could draw it on paper. So, okay, so we know that the new polar coordinates, where that point is right now, is 3.92 inches from the center, and it's 100.511 degrees around the circle. That's where it is now. So let's tell it to convert back to XY coordinates, because that's how we have to move the cutter there, or the ink pen that I have in the spinner and the spindle. Okay, so let's ask for rectangular coordinates this time, or XY coordinates. And we tell it the new polar coordinates. 3 point, always radius first. 3.923. 3.923. Let me give it a few more. 795. And then we put the comma there, so that the calculator knows that we're that's all the digits for the radius, and next is the degrees. And let's tell it 100.511 degrees. Some more digits. 7219. Okay, close the bracket and push equals. And there's our new x coordinate. And you see degrees right here. Negative 0.715. Negative 0.715. Okay. Scroll over. In this case, this is weird, because when you're standing on the right side of the mill, and you're looking at the tilt axis, y is actually z on the mill, and x is actually y, because you're no longer standing in front of the mill. Let's visualize this. So anyway, there's y is actually z, so 3.8579, and you see right there, same answer. Okay, so this calculator does all the trig for you. You're not doing anything more than entering where it was in where a point was in XY coordinates, and converting to polar, and then altering the polar coordinate, one of the two polar coordinates, and then you tell the calculator to convert back to rectangular coordinates, and by entering the new polar coordinates after you altered one of them. All right, so if anybody has a machinist calculator that has the buttons opposite, adjacent, hypotenuse, angle. If it has those 4 buttons, answer me this question. If you can enter any 2 of those pieces of information that you have. So let's say you had opposite and angle, right? Answer me this. If you entered an angle greater than 90 degrees, what happens? What does that calculator do? I don't want to buy the calculator to find this out, and I searched for I went online, tried to find what it would do if you did that. And I can't find the answer. So if somebody would answer that in the comments, that would be great. And I probably can show you how to use, if you already have a machinist calculator, I can probably show you how to do this same thing using those 4 buttons. But I have to know the answer to that question, because that affects the way you would go about it. It might get pretty tricky if the calculator doesn't like things above 90 degrees. The reason it's a question is because it says that Calculated Industries, the one I'm talking about, says that it does right angle trig. And we could always trick it into, I mean, if it doesn't accept anything more than 90, I can't imagine that it doesn't, but anyway, it might be pretty confusing to try to trick the calculator. I don't know. I haven't really thought about that much, but yeah, just if someone would answer that question, we may be able to, maybe that calculator can handle all the way around the circle just fine. Greater, more than just that one quadrant of the circle. So yeah. Alright, so now you know a point can move in 3-dimensional space, and we can always find where it went. One more thing. I don't use this calculator. And I don't do it the hard way either. What I have is I made a program, and it is right here. Plan part 2. Part 1 was just right angle trig, and my part 2 is I can go all the way around the circle. So see where it says A there? It's asking me for the adjacent side length, which would be X. So I would enter, let's just do that tilt one again. In X, that was before we rotate, before we tilt, it was 1.309. Oh, 1.309.033. Okay, so I enter that. Now it's asking me for the opposite. In this case, would be where that point was in Z before we tilted. It was 3.699. And enter that. Okay, see, it's giving me the hypotenuse and the angle there. This is similar to what a machinist calculator does. I give it 2 pieces of information and it finds the other 2. And it's basically doing the things that I did on this calculator, but it's just doing them all, all within the program. It's doing all those functions automatically. As soon as you enter the second piece of information, it just goes. It does all the math. Now it's asking me, it says R equals question mark, the rotation, or in this case, the tilt. So we tilted 30 degrees. So just tell it that. Now in this case, where it says angle, what it gave us, that's the radius, and the hypotenuse is, no, the hypotenuse is the radius. It found that for us, and it also found how far around the circle that point was. That's the angle. Okay, so it's entered at 30 degrees, and it tells us the new X and Y, or in this case, because we would be standing on the right side of the mill, X is Y, and Y is Z. Now it's asking me for V. That's the value of each square if I'm using, if I'm drawing what I'm going to make on graph paper. I can scale the size up or down by changing the value of each square. So I would enter, let's say each square was, I wanted to double the actual size on graph paper. Each square is 0.25, a quarter of an inch. So we want to double the size, so I would enter for value there 0.125 and enter that. And then that's telling me how many squares to count. I put a point there. And because I entered 0.125, it would be double. I would have scaled it up. The plans, the picture I'm drawing of what I'm going to make would be double in actual size by counting that many squares. So 5.7 squares left to the left because it's negative. I would count that far from the, the center, the spot I designated as center on the graph paper, and then I would count up 30.8 squares. Put a dot at those coordinates. Anyway, this is what I use. I programmed the calculator to do this. I'm suggesting this one because this is $20 calculator, and I mean, if you have this calculator, I'll give you the program. You can screenshot it. If you want that, put that in the comments. I'll give you the program. There's better programs though. You wouldn't want mine. I'm not a programmer. It's really not that great. This is just straightforward. Give you the answers. I mean, it's not pretty or anything. So, but if you want it, you can have it. Okay, so when we're standing in front of the mill, and if you're looking downward at the rotary table and the point, well, X is X and Y is Y. Y is going away from you or toward you, X is left, right. Okay, so, but if you go over to the right side of the mill, center, I actually have a dead center in that tilt axis. There it is. So when we're looking at it from this view, and not looking down like this, we're looking at it this way, which is kind of difficult for me to get the camera in there. Okay, we're looking at it from this way, from the right side. So you see now Z up and down. That's now Y, and Y is left and right now. If I move the table, that crank right there, from our standpoint, that is going to move it left or right.